Hello, welcome to part 3 of our lesson on the moments of three, the method of three moments equation, using it to analyze statically indeterminate structures, most especially continuous beam. So in our first two videos, we have started this lesson by introducing, deriving the three moments equation. We have used it to solve two examples so far. So in this particular video, we are going to use the method to solve beams with fixed. Okay, let's start with beams with a fixed end support. So beam that the other example we have solved have been beams with simple support at the end. So what about when we have one end fixed? So how do we handle it? That's what we are going to do. So we do that by looking at example 3. We say analyze and draw the bending moment and shear force diagram of the beam beside, indicating midspan moment in span AB and maximum moment in span BC. Take EI to be constant throughout the span. And so the first thing to note is that since there is moment at support A, so that means MA is not zero. We have two support moments to determine. That is, we need to determine MA and MB. So MA and MB, there are two moments here. That means we need two equations, a 2 by 2 simultaneous equation. But we only have two spans, and with two spans, we can only derive one equation based on the principle of three moments equation. So what do we do? Now, to do in that case, what we do is that we go to where we have the fixed support. We introduce an imaginary span that is actually not there. It's imaginary. So when we introduce the imaginary span, we can now use that span and this span, this other span, to solve, we derive one equation before we now use span AB and BC to derive another equation. That is what we are going to do. So this is what we do. We introduce an imaginary span here. Let's call that span OA. And because it is imaginary, it has a length of 0. So that is what we do. There is no force in that span, so there will not be M over EI diagram. And so for this span AB, this is a M over EI diagram. Because it's a UDL, so we have a semicircle, and the magnitude is WL squared over 8. So we have this place. The central distance, this one, there is no central distance, there is no area. So A1 naught X naught is 0. But for this one, the central distance from B is what? 4, because the whole of this length is 8. From here is 4. So we have A1 X1 to be. What is the area of this? Half base times height. This is, sorry, it's a symmetric, it's not half base. So it's 2 over 3 BH. So 2 over 3. What is our B? 8. What is our H? 80. Multiplied by the central distance, which is 4. So that's why we have this. So it gives us 1706.6. We know our L naught is 0 because there's actually no span there. The moment there is 0, and the length from this one, our L1 is 8, this length is 8 meter. We have calculated the other one. So we go ahead and apply the three moment equation. When we apply, this is the moment equation using span, this span and the other span. So we have M naught 0, M naught L naught, 2MA into L naught plus this. So we go ahead and substitute the values, and give us this because the whole of this is 0, L naught is 0, so the L is 8. 8 times 2 is 16 MA. So the whole of this is 0, this is 6 times this, 1706.5 divided by what is L1? L1 is 8. So that is why we have the 16 MA plus 8 MB minus 6 times this all over 8, in which we can reduce it at MB. We want to make MD the sort of formula. MD equals to minus 160 minus 2 MA. Let's call this equation 1. The next one is to go to now consider span AB and BC, which is what is done here, span AB and span BC. So this is the WL squared over 8, this WA squared over 8. So the central distance from here to here is halfway, which is 4. From here to here, halfway, which is 3 meters. So we can now go ahead and calculate our A1, X1. For this one, our A1 is 2 over 3 BH, 2 over 3 B times H. centralized distance is 4. So we know we have calculated this before. For our A2, B2, our A2 is 2 over 3 times B times H. Centralized distance is 3, so multiply by this 3, that gives us 540. Remember, L1 is 8 meter and L2 is 6 meter. So we write the three moment equation again, which is this in terms of span AB and BC. We put all the value as usual, equate it to this. But remember that MC is 0 because MC is 0 because this place is simply supported. So we come and put MC equals to 0. Having done that, this equation reduces to MB equals to minus 1891.95 minus 8 MB all over 28. We call it equation 2. So if we solve equation 1 and equation 2 simultaneously, this is what we have, that MA equals to minus 55.48 and MB equals to minus 49.16. So by finding our support moment, we can go ahead and use the usual method to calculate to find our support reaction. But let me point out something. In this case, when you are, the first one is to take moment at B to the right hand side. Remember, when you're taking moment to the B to the right hand side, the sign convention will be that clockwise moments are negative and anti-clockwise moments are positive. Now the next one is taking moment from B to the left hand side. What I want to show you, if you are taking moment from B to the left hand side, the first force you calculate, remember this is VA, so this is the one due to VA. This is the one, this is the one component due to our, this is a component due to our this UDL, and this is the one due to this moment that we have here. So we equate it to the moment here, any moment here, and so that gave us this. Take note of that. You can go here and use the upward, the sum of vertical moment to find this other moments at VB. And so we draw a Bernoulli moment diagram and a shear force diagram as usual. Remember, these are first of all plot the moment. This is the moment that we have, and then the simply supported beam. In this simply supported beam, the maximum beam, the moment that midspan we have calculated, which might not necessarily be the maximum moment. But in this one, remember, we were told here to calculate the maximum span moment. And the maximum span moment will not be at midspan. So we need to follow the process again, derive the equations, and find them like we did in other two examples. So this is our final bending moment and shear force diagram for this example. The last case we are going to consider is a case with beams with span overhanging. That's when you have a cantilever beam at the end of a support. For such support, we are going to follow the entire process like we did for one with simply supported. But the only difference is that for this one that is simply supported, we know that the moment here is 0. For this one that has a cantilever, the moment will not be 0, but the moment will be the moment due to the cantilever. In this case, you have a 25 kilonewton load at a span of 1.5. So the moment at this place, because this is an anti-clockwise moment, the moment at this point will be MC will be the one due to this cantilever, which is minus 25 times 1.5 and give us minus 37.5. So whenever you're doing, your MC is minus 37.5. That is what you're using throughout the entire exercise. So we go ahead. You have how many unknown? We know this already to be what? Minus 37.5. We know this to be 0. We only have one unknown and we have two spans. So we can write, use three moments equation by the simply supported moment here, WA squared over 8, which gives us 56.25 here. WL squared over 8 here gives us 36. The central distance, of course, is from the center. This one will be 2.5. This one will be 2 meters. We now go ahead and calculate A1 x1 and A2 x2. Remember, L1 is 5 meters. L2 is what? 4 meters. So we go ahead by doing that. We Where are we? So having done this, the next thing is that we apply the three moments equation. By applying the three moments equation, we have this, in which if we substitute our values, we will have this. But we know MA to be 0, and we know MC to be minus 37.5. So we now substitute. This one will go. With this one, MC is minus 37. So that is why we now put this. So doing that, we are left with only one unknown MB, which we have solved our MB and give us this minus 38.92. So wherever you have a cantilever like this, the moment due to the cantilever, at the moment at that support is just the load due to cantilever. So just multiply the cantilever by the perpendicular distance, and it will be minus because support moments are always minus. So go ahead and draw the bending moment and shear force diagram using doing the as we have done in other example. But take note in this bending moment diagram. By the time you have this place is 38.92, this place is 37.5. The midway will be this plus this divided by 2. But notice that the simple supported diagram for that span is already 36. So if you find this moment from here to here, divide by 2 to half here, is already greater than 36. So if you subtract it from 36, it gives you minus 2.2. What tells you is that the span moment here is still upward, it's not downward. So that was how we have this place to be like this. Take note of that. And so you can go ahead and solve these other examples. Solve these examples to reinforce your understanding of the use of three moments equation. Thank you once again. My name is Engineer Dr. Divyangi Ambrose, and do subscribe to this page channels if you have not done that before. Thank you very much.